Okay, I think we're good again. All right, so the first thing we're going to start with is to define what a function is. All right, so you guys did talk a little bit about this last year, and you were able to go through and look at some different equations and determine if it is a function or not. But does anybody remember what it actually means to be a function? Yeah.
Each x has only one y.
Correct. Yeah. So that's kind of the x and y version of it. Each x has exactly one y. Another way of looking at it, because we don't always have functions that involve x and y. Maybe it's like t and m or something. We could use other variables. So the x we think of as the input, and the y is the output. Okay. So thinking about it with x and y like that, it's not a bad thing, because oftentimes that's how we're looking at functions with x and y. But it's more of an input-output thing in general, though. Okay. So we say there's one output for each input. Like, do you guys remember, I don't know if they were doing this still when you were in elementary school, but those input-output boxes, did you guys do that in math class, like in 5th grade or something like that? Okay. You were learning about functions and you didn't really know it at that point. That's what those were, the input-output boxes, and you're trying to figure out what's the rule or whatever that works if you put this in and you get that out and that sort of thing. That's exactly what that was, though. It's talking about a function. Okay, so now graphically, how did you guys check for functions on a graph? Vertical line test, exactly. So, say it must pass the vertical line test. Okay, and so that's that same exact thing of if it doesn't pass the vertical line test, then you're getting two outputs for one input, and it's no longer a function. Okay, so like if I'm going to do just two quick little graphs here, and we're going to see if we can determine which one's a function and which one's not. Okay, so the first one. Does that pass the vertical line test? Yeah, it does. The vertical line test is you drop a vertical line in it and you make sure that it only ever hits one time, and then it passes. So, yeah, any vertical line that I would drop through this thing, no matter where I do it, each time it's only ever going to hit the function once. Okay, so this is a function. Okay, now what about the second one? Does that pass the vertical line test? No. Okay, are there certain places on that function where it does pass the vertical line test? Yeah, there are certain places where it does, but does every x value work? No. I can find a specific place where it doesn't work. Okay, so for this specific input right here, I'm getting 1, 2, 3 outputs. Okay, and that does not fit the definition of a function then, so that's not a function. Okay, so graphically that's how you can check it out, and we'll be doing a bit of that. Okay, so we're going to move ahead here to domain and range. So what is a domain? Does anybody remember that from Algebra 2? Yeah.
All the possible x values.
Good. Yep, it's all the possible x values that a function could have. Another way of looking at that, they are inputs that work. Okay, that's what we're going to be really dealing with when we're trying to calculate a domain for a particular function, is what numbers, when I plug them in, actually work. Okay, so let's try that for just a second. So if I get f of x equals the square root of x, there are certain numbers that I can plug into this function and it will give me an answer. And there are certain numbers that I plug into this function and it will not give me an answer. Okay? So what are the numbers that work with the square root? What ones am I allowed to plug in? Positive? Squares? Square numbers will work. Okay, that'll give me an integer answer. But I could still plug in, like 3 is still okay, right? It's not a perfect square, but square root of 3 is still a number, right? Anything that's positive, or there's one other number that's not technically positive that still works. 0, right? So the square root, as long as it's not a negative number, right, I'm good. So the domain for this would be all, I'm just going to say non-negative numbers. All right. Mathematicians don't really like to write things out in words, so we can write this a different way. Okay? So instead of writing the word domain, just do the letter D with a colon next to it. Okay, so our domain is, and instead of writing all non-negative numbers, you can do that as an inequality. Okay, so the domain is x and or equal to 0. Does that not describe the same thing? Any number greater than or equal to 0 is non-negative, right? Yeah, so we can do it like that. Now, I'm going to teach you guys a different way to do domain here, a different way to write that inequality for domain that is a little bit more the standard as you move into upper level math, and that's called interval notation. Okay, so I want to kind of pause this domain discussion for a second and talk about interval notation so we can start using it with it. So the way that interval notation works, basically it's a way to take anything that's an inequality and write it in a more concise way. So, and it describes an interval. So, keep breaking my lead. If you use parentheses, you don't include the numbers. And I'll give you some examples here in just a minute to help explain what this is saying here. But just want you to write this down first. If you use the brackets, you do include the numbers. Okay, so let's say I've got the inequality -3 less than or equal to x less than or equal to 5. Okay, we call that a compound inequality, right? And that means that x can be any number in between -3 and 5. And when I have the or equal to bars underneath there, that means it could be -3, it could be 5, right? It includes those two numbers. To turn this into an interval notation instead, it would look like this. put a bracket, -3, 5, bracket. And there's a comma in between. So that means it's the interval from -3 to 5, and because I'm using the brackets, I am including those two numbers. Okay? What if I had -3 less than x less than or equal to 5? So how would that change the interval notation then? Well, up here I said you use parentheses if you're not including the numbers. You use brackets if you do. So what's going to be the only change here? Yeah, the left bracket's going to be a left parenthesis now. So parenthesis, -3 to 5, bracket, like that. And if they were both just less than symbols, then you'd have parentheses on both of them, that sort of thing. Now, this gets a little bit trickier if you've got an inequality that is less than or equal to 2. Okay? Because what are the two numbers? There's only one number. It's just a 2. So x less than 2. Well, what's the upper limit of the interval? 2. It can't go any higher than 2, right? So we know this is a 2, and it's less than or equal to 2, so we put a bracket on that. But what's going to be over here? How far down can it go? It can go infinitely far down, right? Even into the negatives, infinitely far. Okay? So negative infinity is the other one. And I put a parenthesis on there because can you ever get to infinity? No. So can I, it's not an actual number, right? So can I include infinity then? No. So you never put a bracket around an infinity, okay, because it is unattainable. So parenthesis, negative infinity, comma 2, bracket would be that one. Okay. Let's do maybe just one more here, and then we'll start applying this to our domains. What if it was x greater than 1? Take a minute, see if you can write an interval notation for that. X greater than 1. Okay, so what does it look like? Anybody want to be brave? Yeah, go for it. Yes, just like that. So when you have two parentheses on it like that, what does it start to look like? It looks like an ordered pair, right? Like a pair of coordinates. So you got to be careful. Okay, you have to know when you're reading your textbook or whatever, or working on an assignment, in what context are you talking? Are you talking about intervals, or are you talking about points on a coordinate plane? Okay, they look exactly the same sometimes, but it should be clear, based on the context of what you're in, what it is you're actually talking about there. Okay, so all right, well let's do a few more domain problems. And we're going to see if we can write our answers in interval notation. So let's try f of x equals (3 over x). So again, when you're doing domain, you got to think about what numbers can I plug into this? Or maybe the easier way to think about it is, what numbers can't I plug in? And then the domain is everything else, right? So, any numbers that are bad for this one? 0, right. So, as long as it's not 0, though, every other number should work, right? 0 is the only bad number for this. So our domain needs to be anything that's not 0. So what are our intervals? Because there's 2 of them. From what to what?
Negative infinity, 0, 0, infinity.
Yeah, exactly. Negative infinity to 0. All those numbers are good, right? Do I include 0?
No.
Nope. And then there's another interval. Again, I don't include 0. And all the numbers from 0 up to infinity. Both of those 2 intervals are part of the domain. Okay? So technically the way that we describe this is it's the union of those 2 intervals together. Okay? Union means together. So the notation we use, hopefully you made a little space here. We put a little u in between it. Okay? So it's the union of negative infinity to 0 and 0 to infinity is the domain of that function. So that's describing all the numbers in those intervals are ones that are going to work. Let's try do another square root one here. But the square root of x minus 2. So think about what numbers can we plug into that and what numbers can't we plug into that. So maybe start with a little kind of guess and check. Can you put a 0 in? 0 doesn't work because we end up with the square root of negative 2. Can you put it in a 1? Nope. Can you put it in a 2? Yep. No, you can put it in a 2. Because what's it going to be if you plug in a 2? Square root of 0, which is what? 0. So technically that one does work, right? So, and then as long as you keep getting bigger than 2, you're still fine, right? It'll still come out positive. So 2 or bigger, right, is our domain for this. So can you write that as an interval for me? What am I going to start with? Bracket. And then what comes next? 2. And then how far up does it go? Infinity. Yep, we can keep going. And what comes after the infinity then? Parenthesis. Yeah, because we always parenthesis an infinity. Okay, so 2 to infinity, including 2. That's your domain for that one. Good. Okay. This one will be a little challenge to see what you remember from Algebra 2. The natural log of x. Anybody remember what numbers you can put into a log and what numbers you can't? Yeah? Nope. You can put in a 1. It comes up to 0. Anybody else want to hazard a guess? Has to be positive. Okay, this one's sort of like, it's similar domain to that of a square root. Thank you. But you can't put in 0. Log of 0 is undefined. Log of anything negative is undefined. Okay? And we discussed that last year in Algebra 2. So the domain for this is 0 to infinity, but not including 0. Okay? So it would look like that. All right. So a natural log is the inverse of an exponential. So think about how an exponential works. And x and y then are switching roles. It does the opposite. It undoes an exponential. Okay. So last example here. Let's do x plus 3 over the square root of x plus 2. So I start doing like some kind of combination stuff here. So again, you got to think about, what do I have? What are going to be some bad numbers to plug in here? That's going to make it undefined, make it not work. As soon as I see a square root, my attention goes right to that. Okay? So in that square root, ignoring the whole rest of the problem, just in the square root, what works? Anything bigger than what? Negative 2. Okay. So, if it was just the square root, it would be negative 2 to infinity, including the negative 2, right? But look at where I put the square root. If I were to plug in a negative 2, would it work? Why not? It's in a denominator, right? So if this denominator ever comes out 0, that's still bad, right? So negative 2 is not a good number. So my domain then is negative 2 to infinity, but I just don't include the negative 2 then. Okay, that one number is still going to be bad. So it would be this. All right, so when you start throwing some of those little combination things at you, it gets a little trickier, and you got to have to kind of think through it a little bit that way. But always, if there's a mix, start with that and then work your way out from there. In general, there's 3 rules you need to follow. That'll help you with these. We'll discuss in a minute. Yeah.
How come it can't? I thought it could be negative 2.
It can't be negative 2.
So why is it not?
Because parenthesis means you don't include the number. If it was a bracket, that would be bad. The bracket, you include it. Okay, so our 3 rules that we need to follow when we're doing domain work. So we're looking for gaps in the domain, because really we said it's easier to look for what doesn't work, and then whatever else is left over, that's your answer. So gaps in the domain can be created by basically just 3 things. Number 1, and we saw an example of, a couple examples of this, can't divide by 0. So if there's any kind of a fraction in the problem where x is in the denominator somehow, you're going to be playing with that one. Number 2, square roots of negative numbers. So if your function has a square root with x underneath it somewhere, you're going to have to work with that one. Okay, what numbers are going to make the square root have a negative underneath it? And then logs of 0 or negatives. So you're looking for fractions, square roots, or logs. If your function that you're looking at doesn't have any one of those 3 things, the domain is always going to be the same thing. And what's that, do you suppose? What numbers would work? Negative infinity to infinity. Yep. Okay. And a lot of times that's the domain of what you're looking at. When we do that look at all those different functions that you guys are going to present to the class next week, most of them, that's their domain. Negative infinity to infinity. You're going to see that a lot. Okay. The reason I did these kind of functions over here is because these are the ones where then you got to start thinking about, oh, how do I need to change that domain? Because where's the gap? And how's that going to change how I write my domain? So, okay. So that's domain in a nutshell. Range is similar. Range is to y as domain is to x, if you want to think about it that way. So the range would be all of the y values that a function can have. And we don't have a real effective way to do a range calculation by hand, which is good news for you guys, because then you don't have to worry about doing it by hand without a calculator. So what we're going to do is we're going to talk both domain and range by looking at a graph, because you can do that still. Okay, and if you have a calculator, you can graph whatever the function is, and then you can take a look and see what that range might be, as well as the domain too. So let's try once. So let's take a look at the function f of x equals, let's do 1 over x plus 3. Okay, so take out your calculators, open up your y equals menu, and let's type that in. 1 over x plus 3. So it should look something like that. And if you're, just in case, make sure your window is a standard window too, so we're all kind of looking at the same thing here. All right, and then we'll graph that. Okay. So, based on the way that this thing is shaped, we've got some vertical and horizontal asymptotes in here, which you guys studied a little bit in Algebra 2, and we'll talk a lot more about actually tomorrow. But we can use that idea to help us determine what the domain and what the range are. So, now, the domain of this one, if you just look at the equation that we wrote out, you can probably tell me what that is. What's the only bad number in this function for the domain? 0, right? So our domain should be negative infinity to 0, and then 0 to infinity, hopping over the 0, right? And if you look at the graph, just look along the x-axis here. Do you kind of see that domain on the graph? For some people, it's like, boom, right away. Other people, it kind of takes them some time to sift that out. But think of it like this. As we're moving along, I've got value to the function, value to the function. Then as soon as I get to 0, then there's this gap here. And then it hops over the 0, and then it keeps going, right? And that's that vertical asymptote that's at 0. That's what's happening right there, okay? So you got all these numbers up to 0. We hop over 0, and then it keeps going, okay? And that's the x's, okay? So looking at it kind of left to right is domain. Range, on the other hand, would be going from the bottom to the top. Okay, so looking at what are all the y values that I'm getting as I go up, and am I skipping over any as I do that? Okay, so are there any y values this thing never gets to? 3. Yeah, because there's a horizontal asymptote of 3, right? So it goes, hops over 3, keeps going, keeps going, keeps going. So, in range for this, domain, you guys already told me, negative infinity to 0, union 0 to infinity, based on what we saw on the graph there. So what would be the range then? How would I write that? Yep, you got it. Negative infinity to 3, union 3 to infinity, not including the 3. So we're hopping over that one. Yep, that would be the domain and the range for that. Okay, how about a little simpler function, just x squared? Talk domain and range of x squared. So graph that one real quick. Maybe you already know what this one looks like, but just in case, there's x squared. Okay, now keep in mind, x squared just keeps on going, right? So what's its domain? It's everything, right? Negative infinity to infinity. Okay, look at that graph. What's the range of x squared? 0 to infinity, right? Does x squared ever go negative in the y's? So that's not part of the range then. So here's the question though. 0 to infinity, but does it include the 0? It does, because it actually comes down and hits 0, 0, right? That parabola. So it does include the 0. All right, so the domain and range for x squared then, domain is negative infinity to infinity, and the range is 0 to infinity, but we're going to put a bracket on the 0. Like that. Okay? So that's just, I'm not going to do any more with range, but that's just a couple of examples of how you can go at finding a range of a function. Okay? Just look at the graph, think about what y values is it hitting from top to bottom, and you can do an interval just like you do for domain. Okay, with the brackets and the parentheses and all of that kind of stuff. All right. We got a little bit of time. All right, so I can get into continuity just briefly, and then we're going to be done for today. Okay. So, does anybody know what it is to be a continuous function? Say it again. Never ending? Yes and no. It's kind of a more of, not about its start and ending, but more of what's happening in the middle with continuity. If something is continuous, it keeps going, right? There's no breaks in between. Okay? So if something is continuous, think of it this way. It's like you could draw the function without having to pick up your pencil. It just keeps going. But if you have to stop, start again, then that's not continuous. Okay? So let's quickly define that here. So to be continuous, it is a function with no breaks. So think of, you don't pick up your pencil. Okay, so there are some different ways that a function might not be continuous, and that's what we're going to quickly go through here. Yeah?
Another way to say it would be that it has an infinite domain and range.
Its domain would have to, its domain is negative infinity to infinity. I can have functions that have that domain but are not continuous. I'll give you an example. So what if I have a function that starts like this? Say that's an open circle, and then right above it is a solid circle, and it keeps going. Okay, so what this is a function that has a jump. Okay, and in fact, this is the first type of discontinuity we're going to talk about anyway, so that's good. But it's not continuous, right? Because it has to stop and then start again. Okay, but its domain is still everything in there. Okay, had this keep going, so it goes to negative infinity. But let's say this is at, I don't know, 2 or something. Okay, so every number before 2 is included until I get to here with the open circle. Does that include the 2? Open circle? No, it's not including the 2. But is this? Yeah. So I've got every number until I get to 2. I do have 2, and then every number after 2. So my domain is everything. I didn't skip anything in my domain. However, the function is not continuous because I still had to jump to start it up again. Okay? So that's a little bit of a tricky thing to this. It doesn't have to have a domain that's negative infinity to infinity. All right, and so in this first type, discontinuity is called a jump discontinuity. All right, so if something is continuous, or if something is not continuous, it has a discontinuity then. Another kind we'll run into that also does not require that the domain be anything different from negative infinity to infinity would be if I had something like this. If I had a function that had a little hole punched in it, and then maybe the function has a value just like floating above it like that. These are pretty rare, but this is called a removable discontinuity. Okay, so if it jumps up, that's a jump. If you've got a hole in the function, that's a removable discontinuity. And then there's the kind today, actually, and that you guys have studied in the past. It's called an infinite discontinuity, but you know it by a different name. You know it by a vertical asymptote. So we had something kind of like this where it has an asymptote that it's approaching, and then maybe it starts up again on the other side of the asymptote and keeps going. Okay, so what's this object here, this is a vertical asymptote, but the type of discontinuity it is called an infinite discontinuity. All right, so that's it. Those are the different ones we've got. So you guys are going to be asked to identify these in your homework if they give you a function. Sometimes it's just you'll have to graph it on the calculator and look at it, that sort of thing, and we'll get into more of that later. But for tomorrow, we're going to be looking at increasing and decreasing intervals, whether functions are bounded, symmetry. We'll talk more asymptotes, and then we will be done. Okay? So you guys can have the rest of the time to hang out here. Okay, so we're going to start today with talking about increasing and decreasing intervals of a function. And really, we're just going to be doing that by looking at a graph. You're not going to be able to answer these types of questions but just by looking at an equation until you get to calculus. But understanding what those are and what exactly you're looking for is important, though. So let's say we've got a graph here of a function. Let's say it's doing something kind of like this. And this is at, let's say, 1. This is at 5. That's 7. -4. And maybe -6. Okay. So increasing and decreasing. You have to think about like a little point that's moving along the curve of the function, and it's going left to right. Okay? So whenever the little point is moving up on its journey, it's increasing, and anytime it's moving down on its journey, it's decreasing. Okay? So to be able to identify increasing and decreasing intervals, I have to know where the maximum and minimum points are too. So this is kind of related to that extrema thing we talked about. Okay? So I'm going to mark where those are at. So right here is a minimum. Up here is a max. And that point there is a min. Okay, so based on that, can we identify intervals where this thing is increasing or decreasing? And the intervals we want to describe are x values. So from what x value to what x value is it increasing? Or from what x value to what x value is it decreasing? Okay. So can anybody give me an increasing or decreasing interval that you see on there? Mm-hmm.
From -6 to 1 is increasing.
Yeah, good. So we have an increasing interval from -6 to 1. Okay, now there's some debate. You could write it this way with parentheses, or if you wanted to actually include the -6 and the 1 as part of the increasing interval, I guess technically that's true, okay? So I'm going to accept it either way, the parenthesis or the bracket. In this case, it doesn't really make a difference, okay? But that's correct, though. That's an increasing interval. So can somebody else give me another increasing/decreasing interval that you see in the picture there, from where to where? Mm-hmm.
Decreases from 1 to 7.
Okay, decreases from 1 to 7. And again, you could do it with the brackets if you wanted. Okay. And there are 2 more intervals on there still that we haven't done anything with yet. Anybody see where those are at? Yeah, go ahead.
Increasing from 7 to infinity.
Yeah, good. Yep, from 7 to infinity it increases again. Okay, or again, could do it with a bracket. Just remember the infinity, though. It's never going to have a bracket, though, so can't do that. And then there's one more interval that we haven't described yet. Is it increasing or decreasing? It's decreasing from -infinity to -6. Yep. Or again, if you wanted to use the brackets, you could do that. Okay, so good. So like I said, the key is to identify where those maximum and minimum points are, and then using that to set up where is it increasing, where is it decreasing. As long as you think about that, going from left to right, where's it going down, where's it going up, then you got it. Okay. You don't need to worry about y values with this. It's all x, okay, from what x to what x, and you can do it. Now, we can do this on our calculators as well, and I'm going to kind of wrap this into doing it with finding extreme values. Okay, so let's graph a function here real quick. Please do. And we'll do one that's fairly simple here. We'll just have like one increasing interval and one decreasing. Okay, so I'd like you to graph that function for me. X squared plus 2x plus 1. We're going to just do a parabola. All right, and if we go ahead and use a window, standard window, should be able to see it. Okay, so -10, 10, -10, 10. And graph's going to look like that. Okay, so I want to know, where is this parabola increasing, where is this parabola decreasing? Okay, so to do that, again, I got to identify where the maximum and or minimums are on the graph. So in this particular graph, we have maximums, minimums. What's going on? What do you see? There's a min, just one, right? So we got to identify where that minimum is, and the calculator can do that for us. Okay, so if we go second calc, and we can do a maximum or a minimum right here in that same menu where we did the zeros before. Okay, so if we go minimum, it's going to want a left bound and a right bound again. So you're going to move the little cursor along your graph to the left of where you think the minimum is, hit enter, and then it wants a right bound. So you go to the right of where you think the minimum is, hit enter, and then it's going to do a check in between. And the calculator says negative 0.9999999. What is it actually? Negative 1. Yeah. Again, it's doing this weird, not quite getting there thing that it sometimes does. And I don't know if some of your calculators, if the newer models, like, got negative 1 or not, but...
Mine's worse. Mine for the y value has 4.28 exponent to the negative 12 for the y value.
So it's not even giving you a 0 for the y. Okay. Yeah. So sometimes you have to kind of outthink the calculator a little bit, know what it's really trying to tell you, okay? So this is, the minimum is at negative 1, 0, okay? So if I want to know what's the decreasing interval for this, what would be my answer then? Negative infinity to negative 1. Remember, we're just doing the x value. Good. And what's the increasing interval? Negative 1 to infinity. Okay? So you can use the calculator to do that. But you have to use it to pinpoint the mins and the maxes first, and then you can start using that to piece it all together, just the same as we did before. So, okay. So that's that increasing and decreasing stuff. Extrema. Kind of already did it. I'm just going to put in parentheses here maxes and mins. That's really what you're doing. And again, if I give you a graph, can you do it? Also, if you have a calculator, can you type it in and find the maxes and mins as well? Just one thing that we probably need to discuss here a little bit with this is this idea of a relative max and min, okay, versus a absolute max or min. So I'm going to try and draw a function here where we've got all of this going on. Okay, so let's say we got that. This function has two relative maximums and two relative minimums, but it has one absolute max and one absolute min. Okay? And in fact, if I'm going to be real technical here, which I should be, these aren't going to be arrowheads. That's going to stop, and this is going to stop. Otherwise, it wouldn't have absolutes. Okay, so do you guys kind of get what I'm getting at there with that? Two relative maxes, two relative mins, but only one absolute and one absolute for the min and the max. So this point right here, which of them is that? That's a relative maximum. Mm-hmm. So by relative, it means compared to what's around it. Okay? What's in the neighborhood, that sort of thing. Okay? What's close to it. That's a relative max. Now this maximum over here is an absolute maximum. It's also a relative max because it is the biggest thing around. Okay? But it is also the highest point of the entire function. Okay? So this one is an absolute max. But I'll put in parentheses also relative. Okay, and then with the minimums, same kind of thing, right? This is going to be a relative min. And this one over here will be the absolute min. But it is also relative. Okay, not every function, though, is going to have a relative max or min or an absolute max or min. Okay, it just kind of depends. I happen to draw a function that I knew would have examples of all four of those things going on. All right, so I'm going to give you another one, and I want you to see if you can identify relative / absolute maxes and mins, but only give me the ones that exist. Okay, if it doesn't have a certain kind, then you don't need to list it. Okay, so for this one, let's do I'll put some arrowheads on this one. Call that point A. Call that point B. So what is A and what is B in terms of relative versus absolute maxes or mins? So take a minute and try and reason that out. What do we got? Okay, so what's A? It's a relative min. And what's B? And that's a relative max. So, there is no absolute max, right? There is no absolute min. Okay? Now, technically, you could say, well, you wouldn't be right, but I get why you're saying. The relative max is infinity. The relative min is negative infinity. Yeah, but you can't ever actually get to infinity, right? So maximums and minimums are points. Infinity is not a point. You can't get there. So you just say it has none. Okay, there is no maximum. There is no minimum. All right, with those arrowheads, we know it would just keep going up, just keep going down. Okay. Now, if these points, if we had coordinates for these, because they might ask you to do this too. So let's say this is at 1. This is at -1. Maybe this is at -2. This is at 1. So they might ask you, what is the value of the relative min? What's the value of the relative max? When they use the word value, are they talking x or y, do you think? Y. The y is the value of the function. X is kind of like where it happens. And the y is kind of like what you get from where it happens. That input-output idea we talked about with functions, okay? A value of a function is an output of a function. So the y's are the values, okay? So what is the value of the min? Whoops. So the value of the min is -1. And the value of the max is +1, okay? Or they might ask you, what are the coordinates of the min? What are the coordinates of the max? Okay? So in that case, you'd give them the ordered pair, okay? So you got to pay close attention to how exactly they're asking the question, too, okay, as to what kind of information you're going to give them. Make sure you don't give too much or too little, depending on what that is. But, okay, so that's the extrema stuff. Let's see, so we've hit both of those. So, bounds of functions. Okay. This is actually pretty easy. All right. So this refers to the y values in a function. So I'm just going to draw you some quick little pictures here, and I think it'll pretty much explain itself. But if a function is what's called bounded above, that means that there is a certain point at which a function stops growing or doesn't go above. So if I had a function that looked kind of like this, like a parabola opening down, if I draw some line above the function that it never crosses, above the function, we say it's bounded above then. So that type of function would be bounded above. Bounded below, it's exactly the same thing, except I could put a horizontal line below it that it would never cross. So that would look something like maybe I had a function that had a couple little turns in it, but it's not going to go below some kind of imaginary line in the sand down there. Okay, so we have certain functions that are bounded above, certain functions that are bounded below. There are other functions that are what we call just bounded, which means they've got both things going on at the same time. And these are pretty rare. But can you guys think of any functions that you've looked at before that we would call just bounded? Sine wave, good. Yep. So those types that just kind of keep going like that. So we could have a bounded above and a bounded below happening all at the same time. So in that case, it's just bounded. And then there's a fourth case, which is where it's not bounded above or bounded below. And for those, we just call them unbounded. Okay? So I'm actually going to come up here so I don't have to go on to the next page. Bless you. Okay, so unbounded would look something like this, maybe. Are you serious? Pencil, come on. All right, so something like that, okay? I can't put a line in the sand above it or below it that's never going to go above or below. It just keeps going both directions. It's unbounded. Okay? So we're going to come back to this. I remember I said next week you guys are going to be investigating individual functions and then kind of doing little mini presentations on those. So you're going to have to identify the function that you're looking at. Is it bounded above, bounded below, bounded, unbounded, based on the shape of the graph? What do you have going on? Okay? So I'm just going to leave that there. And like I said, we'll investigate that stuff a little further with all of that. But that's what that stuff means, okay? And then finally, talk about some asymptotes. All right. Now, vertical asymptotes. These are created, if you remember from Algebra 2, these are created when they're places where, or they're numbers that would cause the function to divide by 0. So, values of x so basically, I guess in general, they're values of x that caused the function to be undefined. Because of dividing by 0. So I guess a good example of that would be like f of x equals 1 over x. Okay? This particular function has a vertical asymptote. What value of x is going to cause this to be dividing by 0? 0. So this has a vertical asymptote at x equals 0. Okay? So if you are given a function, you're asked to identify all of the vertical asymptotes. That's what you're going to be doing. It's just thinking about looking at the equation and what numbers, if I plug them in, are going to make it divide by 0. All right? So let's do a couple more examples of that and see if you guys can come up with them. So for each of these, just tell me what are the vertical asymptotes. All right, so I'm going to try those 3. The nice thing about this is you only need to worry about the denominator, because that's the only thing that's going to affect whether this is going to divide by 0, right? So I can put whatever craziness I want in the numerator, and it's not going to affect where your vertical asymptotes are. So think of it that way. Just look at those denominators. Where are the vertical asymptotes for each of these? All right. I'd like to give us the first one. 2 over x plus 3. Where's the vertical asymptote? Yeah. -3. Good. All right. Second one. 4. And the last one? 1/2. Yep. Good. Okay. So, like I said, you can kind of ignore what's in the numerator. Just look at the denominator. Pretty straightforward. And a lot of times they're not going to have vertical asymptotes at all. If there's no fraction in the equation where there's x in the denominator, then it doesn't have one, and you're good. So just be aware of that too. Verticals are not too crazy. Horizontal ones are a little bit more difficult to identify. So we're going to spend a little bit of time talking about these. All right, so a horizontal asymptote it's a value of y. Okay, a vertical asymptote is a value of x. So a horizontal is a value of y that a function will never output. But it will approach it slowly. So we're going to take a look at a particular function here on your calculator again. So go ahead and take those out. And we're going to do 2x divided by x plus 1. And be careful of how you type it in. You should have parentheses like that. This particular function has a vertical asymptote and it has a horizontal asymptote. So when you graph that, standard window still should be good. We can make it smaller if we need to, but Okay, so it looks like that. All right, so where, yeah? Yep, it does do that. The 83s will connect the dots here. So it's inadvertently graphing an asymptote, while actually what the calculator is doing is connecting the dots. So it looks like an asymptote. But in any event, where is the vertical asymptote for this one? -1, right? And you can see that in the graph, okay, right here. That's that one place that's going to make that thing undefined. So you can't plug in a -1. There's where the vertical is. Now, take a look at the graph. Where do you suppose the horizontal asymptote is sitting here? Yeah. It looks like it's at 2, right? It's this kind of imaginary line that if you put it through 2, okay, the function is coming up and approaching it, but not quite getting there. It's kind of hard to see because it's all pixelated, but that's the idea. So I'm going to sketch this graph on here so you can kind of see it a little clearer. And we'll talk about this. So we had x equals 2x over x plus 1. And from our graph, we identified that it had a vertical asymptote at -1. And when we sketch these things by hand, we use dotted lines for those. Okay, so there's that vertical asymptote at -1, and then we said that there was a horizontal one at 2. So it's kind of this imaginary line again, make a little dotted line. And then our function was doing kind of this in between them. It was approaching all of these asymptotes in different ways. Okay, so it has that kind of a look to it. All right, so that horizontal asymptote said it's a y value that the function's never going to obtain, or an output it'll never get. Does that make sense looking at that graph? Okay, it's never going to cross that horizontal line. Okay, so it's not going to get there. But it does approach slowly. So as we go out towards infinity, or as we go out towards -infinity, it's slowly approaching that. Okay? So that's kind of what a horizontal asymptote is, how it functions in a graph. Now, how do you determine what the horizontal asymptote is from the equation? Like the vertical ones were easy, right? We just look for the denominator and what's happening there. Horizontals, it's not the same case there. Okay? This one had a horizontal asymptote of 2. Okay? If you look at the equation of this thing, okay, we got a 2x on top, and we got an x plus 1 on the bottom. Think about, what if you put in super huge numbers in for x? Okay? Because as this thing goes out and it becomes super huge numbers for x, we should be getting closer and closer and closer to what value? 2, right? Okay, so let's play that game with this real quick, because we should be getting a 2 if we're putting in super huge numbers here. So put in like 100. Okay, what are we going to get on the top? 200. What are you getting on the bottom? 101. What is approximately 200 divided by 101? It's pretty close to 2, right? Not quite. It can't be exactly that, right? Because it's never going to get there. But it should be very close to 2. Now, if you plug in 1,000, 2,000 divided by 1,001, it's even closer to 2, right? Not quite there yet, but it's even closer. If you put in 1,000,000, 2,000,000 divided by 1,000,001, really close to 2, but not at 2, right? So if you keep playing that game, you can kind of see where it's going, okay? It's called its end behavior, okay? That's why we have that as one of the things we're going to talk about with horizontal asymptotes, because it's kind of all one and the same, okay? So we can identify that the horizontal asymptote of this thing is going to be 2. In horizontal asymptotes, we use y equals instead of x equals because they're y values instead of x values. All right. Now, this super huge number thing, bless you, will always work, okay? But there is a little trick we can use to kind of simplify this strategy up a little bit. This equation in a certain way so that it would have a horizontal asymptote, always. So you've got 3 cases with horizontal asymptotes, with equations of how it might go. So if the degree of the numerator is greater than the degree of the denominator, no asymptote. Okay, so it's going to be what are called rational functions. So it's going to be something over something. So if the top has a larger degree, okay, it's going to, in a sense, grow more quickly than the denominator. Okay, so think about that. If the numerator of a fraction is growing more quickly than the denominator, what's the value of the entire function going to? If the top grows faster than the bottom, then the entire number is going to do what? Get bigger. And it's going to go off to infinity. Okay? So no asymptote. It's not leveling off to anything. It's just going. It's going up. Okay? So if the degree of the numerator is larger than the degree of the denominator, no asymptote. Now, the reverse is true, though. If the degree of the denominator is larger than the degree of the numerator, so let's consider that. I bet you guys can come up with it for me. If you have a fraction where the denominator is growing more quickly than the numerator, okay? Denominator is getting super huge. Numerator, not so huge. Where are we approaching? What value is the fraction getting really close to? 0. When you have a fraction that has a super huge denominator, like 1/1,000,000th, very close to 0, right? It's just a super tiny thing, real close to 0. So if the degree of the denominator is larger than the degree of the numerator, that denominator is going to grow really quick, the numerator not so much, so that fraction then is going to approach 0. And so your horizontal asymptote is always y equals 0. And the third case is the case we've already looked at, is the example I gave you. This one. What's the degree of the numerator? 1. What's the degree of the denominator? The degrees are the same. We've covered the other 2 cases, right? What if one's bigger than the other? But in this case, both degrees, this has a power of 1, a power of 1, that's it. They're the same. The answer for this one was 2. How do you think I could get 2 just by looking at it? Okay, consider this for a second. Oh, did you have an answer? I'm sorry. The coefficient on the numerator, okay. Yep, in this case that's true, but it also relates to the coefficient on the denominator too. If x gets really, really big, does this plus 1 really have much of an influence? No, okay. So if I pretend it's not there, what do I have? 2x over x. Simplify that for a second. 2. There's your answer. you divide the coefficients. Okay? So if I had 2x over 3x plus 1, the horizontal asymptote would be 2/3. Okay? So you have to divide whatever those leading coefficients are on both of them. Okay? So that's our third case. So if the degrees are the same, then you're going to divide leading coefficients. Okay, so let's practice this a little bit. All right. So without even looking at a graph, just the equation. What is the horizontal asymptote of that function? Yeah, -1/2. Good. Tried to fool you there, but apparently Mr. Verberg didn't fall for it. The degree of this is 1, right at the top? Even though I wrote the 3 first, technically the leading term is the x, right? So it's -1 plus 3, really. And so -1 divided by 2, because those degrees are the same, -1/2. Okay. How about 1 over x to the third? Does it have a horizontal asymptote? And if so, where is it? Yeah. 0. Good. How do you know that's 0?
Because the degree on the bottom is greater.
Right. So y equals 0. Good. Okay. I'll do one more. Okay, what about that? X squared plus x minus 1 over x. So what is it? No asymptote. Degree on top is bigger than degree on the bottom. It's not going to have one. Okay, so related to all this stuff, I'm just going to briefly talk about end behavior. Okay, so end behavior is where is the function headed? And a horizontal asymptote is the end behavior of a function. Okay, it's really just the writing out the answer as a limit that is confusing. We're really not going to do a lot with limits until the very end of class, so this is kind of like a one-shot thing, and then we will kind of get away from it a little bit. But, like, well, let me just write down the definition here first, and then we'll go to the next page, and I'll kind of show you what I'm talking about. So if you want to think of it as where's the function headed, and the answer is going to be a y value, and we're going to consider both as x, and the little arrow here is approaches. So as x approaches infinity and x approaches negative infinity. Okay? So every function has, well, not every function, but most functions have two end behaviors. As it goes to negative infinity, as it goes to positive infinity, where's it headed? All right, so let's try it. So I'll give you a graph here. Okay, we'll call this f of x. So, give you what appears to be some type of exponential type function. And so we have both a left end behavior and a right end behavior of this thing. So the left end behavior is going to be as x approaches negative infinity, what is happening to y? Where is it headed? Okay, and the way that we write that out is in what's called a limit. And so this is what it looks like. This is the notation. So we just use an abbreviation lim for limit, and then underneath it, really tiny, we have our as x approaches negative infinity of f of x equals the answer. Okay? So, yes, I'm going to make you write this out every time. Limit as x approaches negative infinity of f of x equals what? Okay, so what's going on here? As x approaches negative infinity. So now we're going to move a little point along the curve from right to left. So as we go right to left, where's it headed? Up to infinity, right? So the answer to this limit, or the left end behavior of this particular function, is infinity. That's how you would write it. Now, the right end behavior, we have a what that we just got done talking about? Horizontal asymptote. And the only difference in how we write out the limit for the right end behavior is now it is the limit as x approaches positive infinity, okay, of f of x. Okay, and so then what would be the answer to that? As x approaches infinity, where's the function going? To 1. So that would equal 1. So end behaviors, sometimes it equals infinity, sometimes it equals negative infinity if it's going down, sometimes it equals a number if it has a horizontal asymptote. Okay? So that's how you answer those questions about the end behavior. And I believe all of the end behavior questions on your homework assignment are either you graph it on the calculator and look at it, or they have a graph provided for you. You don't have to see the graph in your head to be able to do it. Okay? Unless it's one that's a horizontal asymptote, then I suppose you could, but I try to make it a little bit easier for you. Okay, that's all I got. So remainder of the time here, you guys can work on some homework, and we'll get started with that.